You're not going to see any past paper questions on this, so make sure you practice this separately. So, I mean, this is, I'll just briefly go through this. I told you that there's a thing called mass spectroscopy. What happens in mass spectroscopy is that you take a molecule, and let's say you take a CH3Cl molecule and you ionize it. And when you're ionizing it, what happens is you're bombarding it with electrons, and so that it turns into a +1 ion. But at the same time, the CH3Cl might break down into tiny fragments, right? Lots of tiny fragments. So the CH3Cl might break down into a CH3 +1, or the Cl might break off, or the CH2 +1 might break off. So lots of tiny fragments can be formed, and these are known as your small fragments. And then what you did was you took this molecular ion and all the other ions, and you passed them through a magnetic field, and they would get deflected. The heaviest one was your molecular ion, and it would get deflected in the magnetic field. And when it will get deflected, deflection is inversely proportional to mass. So lots of tiny particles are going to be formed. Just a second. So lots of tiny particles, the tinier particles would be deflected more because deflection is inversely proportional to mass. So, and the heavy particle, the molecular ion, will have two different masses. Why would it have two different masses? Siddha, can you hear me? Sorry, just a second. So it will have two different masses. This one, क्या था last class में? This one. Hello.
Yes, sir.
हाँ, मैंने कहा ये हमने क्या किया था last class में?
या सर यही मास स्पेक्ट्रोस्कोपी का आपने सारा बताया था, आइसोटोप्स बता दिए थे सर, प्रोबेबिलिटी उसका रह जाता.
Okay. So I told you that Cl has a mass of 35. Cl has two isotopes. So I told you that the molecular ion, we are interested in the heaviest ion. It will have two different detections, and it will have two different masses. Why? Because either one of the Cl would be 35 or the other one would be 37. So if it's 37, the molecular ion will have a bigger mass. It will be heavier, and it will be deflected less. And if it's the smaller ion, it will be a smaller isotope. It will be deflected more because it's going to be lighter. And I told you the probability. What's the probability of getting Cl35? That was 3/4. And what's the probability of getting Cl37? That's 1/4. Is this clear up till this point? Ye clear hai? Is this like clear? Raid, Osma, Umar, Saim, is this clear? Is one clear?
Sir, could you explain the M+2 and M?
Okay, I'll talk about. But this part is clear, right?
Yes, I'm able to understand it.
Okay, so your mass spectroscopy would kind of look like this. You'll detect something at 50, you'll detect something at 52, and then you'll detect a lot of random small particles, which are basically fragments of the original molecule. So lots and lots of fragments are going to be produced. Now, and the ratio would be 3:1 because Cl35 has a much higher probability, 3/4. Cl37 has a much lower probability, which is 1/4. So anyways, what's the M and what's the M+2 peak? So the M peak is, M stands for molecular ion. So instead of calling it 50, the peak at 50, it's just a way of referring to peaks. Instead of calling it the peak at 50 and the peak at 52, you call the lighter version of the molecular ion as the M peak, right? And the heavier version is 2 more than it's heavy by what number? By 2, right? So this one is the M+2 peak. Tanya, is that clear?
Yes, sir. Yeah.
If it had been 55, then it would be the M+5 peak. So all the molecular ion peaks are known as the M peaks, but this lighter one is going to be the M. The other ones would be either M+1 or M+2 or M+3, depending on how heavy they are. So anyways, so whenever you see a mass spectroscopy, so you're not going to get all of the above. You'll see this thing. Whenever you see this thing and you see a molecule, the heaviest peaks having a ratio of 3:1, that clearly indicates that the molecule has 1 Cl. So that is evidence that the molecule has one Cl. So you'll figure out that the molecule has a Cl atom. The other thing is, what if the molecule has two Cls? So it could be any molecule that has two Cls. So if it has two Cls, so this is CH3, I mean, this is the molecule. If you ionize it, it will turn into a CH3, CH2, CHCl2 plus one ion. That's the heaviest one. That's the molecular ion. And then there would be lots of tiny charged particles, which are the fragments. These fragments are bits and pieces of this bigger molecule, but they are lighter. The fragments are always lighter. So the fragments are going to be deflected more. So there would be all sorts of detections, lighter detections, and the fragmentation is completely random. You don't know how the pieces will, how many pieces will be formed, or whether CH3 will be, I mean, so the fragmentation pattern is completely random. This thing is completely random. So we're interested in the heaviest peaks. We're interested in this thing. We're interested in the fact that this molecule is going to have, it's going to have three different masses. The molecular ion, there would be three different molecular ion peaks because the particle will have three different masses. Why would it have three different masses? Either both of the carbons are 35. So, I mean, the CH3, CH2, and CH part, that gives you 42. And the two Cls could be 35, so the mass would be 112. So that's a lighter version of the molecular ion. Or one of the chlorines is 37, has a mass of 37. So 42 plus 35 plus 37, that gives you 114. So that's two more. So it's M plus 2. And then there would be a very heavy one, which is 42 plus 37 plus 37, that's 116. So your mass spectroscopy will give you three very heavy peaks, M, M plus 2, and M plus 4. Is that part clear? If you have two Cls, there would be M plus 4 peaks as well. Is that clear? Yes or no? Is this clear?
Yes, sir.
Bakio clear? Rizwan, is this clear? Oswa? So now what we'll do is, we'll try and figure out what is the probability. It's 9:6:1, but how did we get there? We got there because what was the chances of getting Cl35? That was 3 by 4, 75%. What was the probability of getting the other Cl35? That's 3 by 4 as well. So if you know basic probability, whenever you have an AND, probabilities get multiplied. And whenever you have an OR, probabilities get added. So over here, the first one is Cl35 and the second one is also Cl35. Cl35 and Cl35. So it's going to be 3 by 4 into 3 by 4. That gives you 9 by 16. So the chances of getting the M peak is 9 by 16. Probably greater than half. It's, I mean, around 55%. Or if you have 16 events, 9 out of times, if you detect 16 particles 9 times, you're going to detect 112. Then what are the chances of getting both of them as 37? The first one is 37, Cl37, and the second one is also Cl37. So Cl37 and Cl37, that's 1 by 4 into 1 by 4. That gives you 1 by 16. So detecting this has a very low probability. Out of 16 times you detect a particle or a molecular, and there's only one chance that it's going to be 116. And then the middle one of them is 37. The first one is 35. Now this one has two events. So the events are, it's Cl35 and Cl37, or there's another event. The first one is 37 and the second one is 35. In both cases, you're going to get a mass of 114. So there's an OR in the middle. It's either Cl35 and Cl37, or it's the first one is Cl37 and the second one is Cl35. So the probability comes out to be 6 by 16. Or you could simply have subtracted 1 by 16 and 9 by 16 from 16. You would have gotten 6 by 16. Or from 1, you would have gotten 6 by 16. So is this clear? The probability is 9:6:1. Is this clear?
Yes, sir.
Okay, Bakio, clear? Sidra, is this clear? Simon, Rizwan, clear? Read. Okay, so just remember 37 and 37. So just remember 37 and 37, 1 by 4 into 1 by 4. 35 and 35, that's 3 by 4 into 3 by 4. This one, two different events. Either this one is 35, this one is 37, or this one is 37, this one is 35. So you add this up, or simply you add these two up and subtract from 1, you get 6 by 16. But anyways, so whenever you see a graph like this, a mass spectroscopy, and whenever you see, forget the fragments, whenever you see the heaviest peaks, and there are three of them, there's M, M plus 2, and M plus 4. There's a difference of 2 between them. And the relative ratio is 9:6:1. That kind of indicates that the molecule has, it confirms that the molecule has 2 chlorines. Okay, so that's how we figure out a molecule has chlorines, because no one has ever seen a molecule actually. No one has ever actually seen an atom as well. Most of it is just guesswork based on this. So you can't really take a picture of a molecule. So this is the picture of the molecule. When you see this says that there are 2 Cls in the molecule. Anyways, the same applies to bromine as well. So bromine has 2 isotopes. It's got an isotope which is 79, and it's got an isotope which is 81. And both of them have equal probability. It's 1 by 2, and it's like a coin toss. So if you have a molecule, either it's going to have bromine 79 or it's going to have a bromine which is 81. 50-50% chance of getting either one of them. So let's try and figure out the mass spectrum of a molecule that has 1 bromine. If it's got exactly 1 bromine, it will have 2 different masses. The molecular ion will have 2 different masses. Lots of fragments, but the molecular ion will either be 12, that's carbon, 3 hydrogens, and then there is 79. So it's either going to be 12 plus 3 plus 79, that's 94. Or it's going to be the other isotope. It's going to be 12 plus 3 plus 81, and that's 96. So it will have 2 different masses, an M peak and an M plus 2 peak. And both of them will have equal probability. So your mass spectrum would kind of look like this. The heaviest peaks would be, the heaviest particle detected, 94 and 96, M plus 2, molecular ion peak, will have equal heights. If you detect 200 particles of this, there would be 200 particles of this also detected. Both of them would have equal probability. Is that clear as well? Clear? Tanya, is this clear? Rizwan, Sidra, is this clear?
Yes, sir.
So this one is basically the exact same math, except that over there it was 3 by 4 and 1 by 4. Now you have 1 by 2 and 1 by 2. And the same thing when you so whenever you see a mass spectrum that looks like this, it's got two heaviest peaks and they have the same ratio. That means it clearly indicates that it's got 1 bromine. The last one is not the last actually. What if a molecule has 2 BRs? So 2 BRs, then you will have an M plus 2 and M plus 4 peak. The molecular ion will have 3 different masses. Either both of them would be 79, or one of them is going to be 79 and the other one is 81, or both of them would be 81. So it's going to be either 172, 174, or 176. So there would be 3 different masses. What is the probability of getting the first bromine is 79 and the second one is also 79? So that's half into half. That's 1 by 4. What's the probability of getting 176? First bromine is 81 and first bromine is 81 and the second one is also 81. So it's half into half. That would give you 1 by 4. What's the probability of getting 79 and 81? So it could be the other way around as well. The first one is 81 and the second one is 79. So it's half into half plus the other one, half into half. In both cases, you're going to get 174, and that's 2 by, so that's going to be 2 by 4. So what's happening is the relative ratio is going to be, so what's happening is that the relative ratio is going to be 1:2:1. Okay, is that clear as well? It's going to be M plus 2, N plus 4, and the ratio would be 1:2:1. Is that clear?
Yes, sir.
Acha, so the summary is, here's one thing, that's the basic point. If a molecule has one BR, then it's got an M plus 2 peak only, and the ratio would be 1:1. If a molecule has two BRs, it's going to have an M plus 2 and M plus 4 peak, and the ratio would be 1:2:1. Same with Cl. If a molecule has one Cl, the M plus 2 peaks, and the ratio would be 3:1. And if the molecule has two Cls, then M plus 2 and M plus 4, and the ratio would be 9:6:1. So that is the summary. By just looking at the graph, you see this, that clearly indicates it's got one Cl. You see this, it clearly indicates that it's got two bromines, 1:2:1. As if you see, that's again bromine. So and then there's another third scenario, which is, what if a molecule has one Cl, it's got both of them, and remember, the combinations could be endless. What if the molecule has three Cls? Now mass spectroscopy, the way it works is that there's a computer that does all the calculations, and it will exactly tell you if a molecule has three Cls, it's going to look at the peaks, and the computer will tell you. So we're not going to go into that much detail. We'll just limit ourselves to one bromine or two bromines, or one Cl or two Cls. We're not going to be talking about CCLs. We just want to learn the idea of how a mass spectroscopy, or how does a computer figure out that a molecule has chlorines and bromines, and in what number. Now the next one is, what if a molecule has one Cl and one Br? If it's got both of them, then it's going to have an M plus 2 and M plus 4 peak with ratio 3:4:1. So for the chlorine, there are two options. It's either 35 or 37, and the probabilities are given. And for the bromine, it's going to be two options, either 79 or 81, and the probabilities are given. So if you have the molecular ion, which is this, the math is done. It's kind of the same math. Either you'll have a lighter version of the molecular ion, which is bromine would be 79 and chlorine would be 35. And the probability of that is half into 3/4. That gives me 3/8. So there's a 3/8 chance of getting the lighter version of the molecule. Then a slightly heavier one, just by 2. So if you want to increase the mass by 2, then it's either going to be 79, and instead of 35, it should be 37. Or the other one, it's either going to be 81 instead of 79, and this would be 35. In both cases, the mass comes out to be 130 or M plus 2. And the probabilities would be half into 1/4, and this would be half into 3/4, which is done over here. And that gives you 4/8. And then
sir,
yes.
Is it always chlorine and bromine, or will they give us other elements too?
I'm going to come to that. The reason, I'll just quickly tell you why you can do this with chlorine and bromine, because chlorine and bromine have isotopes that are very abundant. Do you get my point?
Yes. Yeah.
I mean, for example, hydrogen has isotopes, right? I think I did tell you isotopes. Just a second. So just as an example, there could be a variation in mass because of hydrogen as well, right? I mean, that's a possibility because hydrogen has isotopes. But what is the probability of getting hydrogen too? That's like almost non-existent, right?
Yes. Yeah.
So your mass spectroscopy will barely detect any variation due to hydrogen, because that particle will not be detected because it won't be there. I mean, there's a very small chance that it will ever be detected, right? I don't know what 0.001% is. Like if you detect like 1 million particles or 10,000 particles, then there might be one that will have hydrogen too, right?
Yeah.
So the variation in mass because of other elements is so negligible that your detector will never detect them. I mean, the peak or the height would be so small, so tiny that you wouldn't be able to see it.
Okay, I see.
So that's why chlorine and bromines are important, and we're going to bring in carbon into this as well.
Okay.
Basically, mass spectroscopy works for those elements who have abundant isotopes. Like you can work with their probabilities, right? Like 3 ratio,
Yeah.
4 ratio. I mean,
Under-
so you can kind of work with the probabilities.
yeah.
If the probability is close to 100%, then I mean, obviously the probability is not going to help you.
Okay. Okay. Understood.
Okay, so is this clear that it's the same math? It's just that there's one bromine and one chlorine now.
Yes, sir. That's understandable now.
Okay. So is this clear? Right, there's one. Omar, is this clear? I'm clear.
Yes, sir.
So next one. So that's about it. So all you have to do is just, I mean, most of the time you just remember this. They have not, but they might ask you to do the math as well, but they haven't. All you have to do, I mean, make sure you know at least this, that m plus 2, m plus 4. If you see something like 3 ratio, 4 ratio 1, the heaviest peaks, that would indicate, I mean, lots of tiny fragments, but the heaviest ones, 3 ratio, 4 ratio 1, that clearly indicates it's got one chlorine and one bromine. Now, the next thing is, another very important factor is that you can also figure out the number of carbon atoms based on this. Now, the probability of carbon is this. Carbon 13 has a very low probability, but it's still detectable. Like there's a 1% chance. So out of every 100 particles, there would be one that will have carbon 13 in it. So it's not that less, but you can detect it. So it's like 99% versus 1%. So most of the time, you're going to get carbon 12 in the molecule. So if I have, now based on this, I will be able to figure out, just like I figured out the number of chlorines and bromines, in exactly the same way, I'm going to figure out the number of carbons as well. Now, carbon, let's assume an atom that has carbon, that has exactly one carbon atom. And let's ignore that there is no chlorine and bromine. There's going to be a variation in mass because of the isotopes. So most of the time, there's a 99% chance that the mass of this particular methane molecule is 16. Because the carbon is 12, 1 plus 1 plus 1, that's hydrogen, right? And then there's going to be an m plus 1 peak. I mean, this is an m plus 1 peak because it's greater than 1. So, I mean, it's the mass difference is plus 1. So there's going to be this slight small m plus 1 peak. What's going to happen in that m plus 1 peak is it's got carbon 13 in it. So what's the probability of getting carbon 13? That's approximately 1%. What's the probability of getting carbon 12? That's 99%. So when your mass spectroscopy detects these particles in lots of smaller fragments, for ignoring the smaller fragments, so it's going to have a detection at 16. So most of the particles detected would have a mass of 16. So 99 particles would be detected having a mass of 16. And just one particle getting detected, which will have a tiny mass of, I mean, not a tiny mass, the heavier one. Just so it's 99 ratio 1. So if you have 99,000 particles of this, there would be 1,000 particles of this. So is this clear? This thing?
Yes, sir.
But how does it? So let's move to the next one. What if? And you'll notice a pattern. What if you have 2 carbon atoms? Now you'll have an M peak and an M plus 1 peak and an M plus 2 peak as well. So what if you have 2 carbon atoms? So what will happen now is, what's the chances of getting both of them as carbon 12? Carbon 12 and carbon 12. That's 99% into 99%. If you do the math, this comes out to be 98%. So the probability of getting the M peak is now 98%. What's the probability of getting 31, the M plus 1 peak? So it's either this one is carbon 13 and that one is carbon 12, or that one is carbon 12 and this one is, so there are 2 events. So it's 99% into carbon 13, which is 1.1%. And since there are 2 events, you multiply it by 2. And if you do the math, it comes out to be 2%. And then what's the probability of getting carbon, both of them as carbon 13? So both of them as carbon-13 would give you M plus 2 peak, and that's 1.1% to 1.1%. That is a very low probability. So this M plus 2 particle is barely detectable. So you can safely ignore this, which is why I'm cutting it out. Why? Because I mean, both of them as carbon-13 is almost negligible or non-existent. Is that clear? You clear?
Yes, sir.
Okay. So which is why we don't care about the M plus 2, because it's hardly detectable. There's almost zero chance of getting the, and remember, this is percentage. The actual I mean, if you divide by 100, the actual probability would be even lesser. So M plus 2, I mean, you can sort of cut it out. You're never going to detect that. So it's basically 98% and 2%. So look at the pattern. The pattern is, when you had one carbon atom, the relative heights of the MM plus 1 was 99:1. But when you had two carbon atoms, the relative heights are now 98:2. So you would see a pattern. As the number of carbon atoms increase, the height of the M peak is decreasing by 1%, and the height of the M plus 1 peak is increasing by 1%. Is that idea clear?
Could you explain that again, sir?
I mean, is this calculation clear, Tanya?
Oh, yes, yes, sir.
So what I'm saying is, you're noticing a pattern. This molecule had one carbon atom, right? I mean, the methane molecule.
Yes. Yeah.
So what was the relative height, MM plus 1 ratio? That was 99:1, right?
Mm-hmm.
But when the molecule had two carbon atoms, what's the relative heights? It's 98:2, right?
Yes. So it's increased. Oh wait, no, it's decreased and then increased.
The
Okay.
one of them, the M peak is decreasing and the M plus 1 is increasing.
Yes.
So that means, as the number of carbon atoms keep on increasing in a molecule, the M height starts to decrease. So what if the molecule has three carbon atoms? What will be the M height now if it had three carbon atoms based on the pattern?
Well, 97 and M plus 1 will be 3.
3. So even if you do the math, that's exactly what will happen. So if a molecule has three carbon atoms, right? So what's the probability of getting all three as carbon-12? It's carbon-12 and carbon-12 and carbon-12. So it's 98.9% in 3 times. That approximately comes out to be 97%. What's the probability of getting one of them as 13? So that's 3 events. Either this is 13 into this, or this is 13. So that's 1.1% into 99% times 3. That would give you 3%. And so on. So if a molecule has 4 carbon atoms, it's going to be 96:4, right? If a molecule has 10 carbon atoms, it's going to be 90:10, right? So based on this trend, by looking at the M plus 1 height, you can calculate the number of carbon atoms. Okay, so you can do that. But there's a problem, and that problem is that they'll never use these ratios. I mean, they wouldn't say 99:1. Because if they had told you 99:1, then it would be very obvious. You can figure out the number of carbon atoms, right? Or if they had, and this applies to all the above as well. If they told you 97:3, so 97:3 is what? It's I mean, 97:3 is 3 carbon atoms, right? But the ratio would be given in this way. I'll just explain quickly. It would be given. Wait a second, I'll just do some math. So it would be, I mean, you'll be given this ratio. Let's say it's 48.5 ratio 1.5, right? Now, when you look at 48 ratio 1.5, it's pretty hard to actually figure out, is this 97:3? Because the ratio is exactly the same. Do you get my point?
No, sir. Can you explain that?
I'm just saying that how did you figure out that this has 3 carbon atoms? You looked at the ratio, right? It's 97 ratio.
Yes.
When you see 97 ratio 3, you would know it's 3 carbon atoms, right?
Yes.
But the point is, they're not going to write 97 ratio 3. They're going to write 48.5 ratio 1.5.
Oh, okay.
Now this ratio is exactly the same. It's 97 ratio 3. I mean, if you
Simplify it?
huh?
Or how do you times it by 3 or simplify it? I mean, how do you
No, you're
then that
saying how did I figure out that this is 97 ratio 3?
Yes. I mean, with these values, 48.5 ratio 1.
I mean, you can. How do you find the simplest ratio? Divide by the smallest. What's 97 ratio 3? If you divide by the smallest, what's 97 divided by 3?
1 second. 97 divided
That's
by
good.
3. 32.3.
And it's going to be 32.3 ratio 1, right? 3 divided by 3 as well, right?
Yes. Yes.
Do the same over here. 48.5, 1.5. Divide by the smallest. Divide by 1.5. This one is 1.5 as well.
Okay.
And I think you're going to get the same thing.
48.
Divide by 1.5.
Yes. Yes, sir.
So that kind of makes things confusing. I mean, my point is that kind of makes things confusing because of the fact that, I mean, analyzing 97 ratio 3 is easy because you did the math with this thing. But the mass spectrum would give you ratios, and it could give you any ratios. It could give you 48,500 with 15,000, right? So, but that would be the same ratio, 97 ratio 3. So do you get my point that the number that they will give will make things confusing? So there's a simple formula for doing that. You can either do the math or there's a simple formula for that you can figure out the number of carbon atoms by using this formula. 100 over 1.1 into the m plus 1 height divided by the m height. So if they give you this number instead of 97 ratio 3, and they'll probably give you some random number like this, but the ratio would be exactly the same. So what you'll do is plug in the m plus 1 value. So this is going to be 100 over 1.1. M plus 1 is 1.5. And the m is 48.5. Now try calculating this. This will directly tell you the number of carbon atoms. I mean, is somebody doing this? What do you get for this?
I got 2.81.
And you're going to round this off. So this is basically
3. Okay.
So instead of worrying too much about the ratio, whatever value that they give, remember the ratio would still be the same, whether they give you 48.5 ratio 1.5 or whether they give you 97 ratio 3. You just plug it in the formula and you'll find out the number of carbon atoms directly. So we'll try and do some math using this. 1 second, where's the some questions, past paper questions. This is and remember this was previously part of A2, so I have to open up an A2 worksheet. Make sure you remember this because people forget when they're doing past papers that, I mean, because you won't see any questions similar to these. It's a new topic that's added, so let me just, not sure where the worksheet is. So it's open. As anyways, I'll just do some questions related to what we've just studied. Number of chlorines, number of bromines, number of carbon atoms, all can be figured out. I said we haven't talked about fragments at the moment. So let's have a look at this one. See, there is the information that's given over here. Ignore the other question, but the whole question, but just this part. You've got an M plus 2 peak, and the ratio is 43.3 ratio 14.1. So M plus 2, what do you think this ratio is? What is 43.3 ratio 14.1? Well, if I go back, remember, carbon depends on the M plus 1 peak. This question is not about the M plus 1 peak at the moment. It's M plus 2. So let's compilate. Where's the... See this one. If a molecule has 1 Cl, it will have an M plus 2 ratio of 3 ratio 1, right? So come back over here. It's M plus 2. Is this 3 ratio 1? I think this is 3 ratio 1, right? 43.3 ratio 14.1. That's 3 ratio 1. So that means 1 chlorine is present.
Yes, sir, it is. Yeah.
Okay, so that means it's got 1 chlorine. बाकी वो clear है? Sign clear है? Ray, there's 1. Sidra.
Yes, sir.
So it's got 1 chlorine. So it's pretty simple. It's not, I mean, it's not rocket science. You just, I mean, they just give you this, you just tell them that it's got 1 Cl. They might, what element is indicated by the M plus 2 peak? It's got 1 Cl. That's what it indicates. And then there is the M plus 1. The M plus 1 is used to figure out the number of carbon atoms, right? And remember, they didn't use 90 or something. It's 43.3 ratio 3.35. So you'll just plug it in the formula, which is, how do you figure out the number of carbon atoms? It's 100 over 1.1 into the M plus 1 height, which is 3.35, divided by the M height, which is 43. So which is so M plus 1 divided by M. This is the formula, which is number of carbon atoms, M plus 1 divided by M. Can somebody do the math and tell me how many carbons it's got? M plus 1 divided by M into 100 over 1.1.
$7.03, sir, which is, I think, 7.
So it's got 7 carbon atoms, right?
Yes.
So you figured out 2 things. It's got a Cl present, it's got 7 carbon atoms present, right? This is not in your course. That's NMR spectrum, that's A2. But anyways, we'll do questions similar to this. Here's another one. So tell me the number of carbon atoms. It's going to be 100 over 1.1 into M plus 1, which is 0.22, and divide by 5.1. So what do you get?
3.92, which is 4.
So this molecule, whatever this molecule is, it's got 4 carbon atoms. Just remember, NMR is not in your course. TK, NMR is not in your course, and no past paper will have. So the only thing that's in your course is this M plus 1, M plus 2, M plus 2, M plus 4. That's the only thing that's in your course at the moment. And you won't see anything in your past papers. You're going to see this in the A2 past papers, but not in AS past papers. So what else? Now over here, he's saying that there is an M plus 2 peak of similar height to the M peak. So when is the M and M plus 2 height of similar, they have the same ratio? When do the M plus 2 have the same height? If a molecule has?
Br, bromine.
They would have the same probability, 1:1. So that one is, so that kind of indicates it's got 1 PR. And again, you have an M+1 and so you can just, I mean, you can figure out the number of carbon atoms, 100 over 1.1 into 0.2 divided by 5.9. Whatever, you can just find that out on your own. So that's kind of about it. That's pretty much it. I'll just briefly talk about, I'll just finish this. I'll just briefly talk about the fragments as well. Okay, just very briefly. Achha, one other thing is you can figure out the MR as well. I mean, that's pretty obvious. That's the molecular ion mass. So you can figure out the MR. And there's one last thing that needs to be told is that the fragmentation pattern. Okay, let's talk about the fragmentation pattern in the next class now. Okay, we'll talk about that. It's going to take some time. So we can't really do that, but I'll just briefly tell you that the fragments is like a puzzle. Like if you a puzzle is like a small pieces of a bigger molecule, right? So when you have, sorry, just a second. As I said, let's continue in the next class then, okay?
Thank you, sir.
Okay then, take care.